All right. Last day, we ended off talking about or introducing the concept of Lewis dot configurations. Gentlemen, you need to track. Lewis dot configurations are essentially the same thing as board diagrams, with the exception that Lewis dots ignore any interior completed shells. So it's only concerned with the valence electrons. Yes, sir?
If we're drawing a Lewis dot compound,
Yep.
is it imperative that we include all of the dots, even if we've already compounded the two?
There's a, when you draw Lewis dot diagrams, if you have a chemical bond between two atoms, what you can do is instead of showing the dots, you show the bonds, a line instead of the two dots.
But the ones outside of it? Like,
Yes.
Okay.
Yeah, you have to show, and what you should see is you should see that all of the suborbitals are actually filled, and I'll show what I mean in a second. Okay, so for example, just to take a step back in time, we looked at the example of the ammonium ion. And we said that there's a certain protocol that you follow in order to do compounds. And that is number one, is that you have to list all of the, yes?
She doesn't have a copy yet.
At the end, I'm going to give you a copy. Okay? I don't have blank copies, and you don't want a blank copy, actually. So what you have to do is you have to list all of the electrons that are involved in this bonding. And so nitrogen, if you look at your periodic table, and this is your first step, is you have one nitrogen, and if you look at your periodic table, you can see that there's 5 electrons in the outer shell. So 1 times 5 is equal to 5. So from the nitrogen, you're going to have 5 electrons involved. This tells me I've got 4 hydrogens, and there's 1 electron in the outer shell of hydrogen. So I've got 4 times 1 is equal to 4. So if it was just NH4, period, you'd have a total of 9. But what this says is that this is an ion, which means I've lost a single electron. And so I have to lose 1 electron. So now I've got 8 electrons all day. So that is the first step, is determining total number of electrons in play. The second step is to draw a symmetric representation of the molecule. So if you have 1 nitrogen and you've got 4 hydrogens, the most symmetric configuration is to put the nitrogen in the middle and surround it by 4 hydrogens. So that's what I did. That's step 2. Step 3 is to add enough electrons, are you hearing me, around the central atom to complete the octet, or 8. So I did 1, 2, 3, 4, 5, 6, 7, 8. And then any additional electrons are going to be put surrounding the other electrons. But here's the thing. In this case, I have used up all 8 electrons on the nitrogen. So the big question is this correct? Or another way of saying it, is each atom happy? Keeping in mind the octet rule, which states that all atoms seek to gain 8 electrons in its outer shell by whatever means necessary, we can see that nitrogen is. He's got 8. What about hydrogen? Well, it turns out that hydrogen is so small that it only has 1 outer shell, and its maximum to be filled is 2. Therefore, every one of these hydrogens is actually happy as well, because they all have a full electron shell. How do you know that your Lewis dot diagram is correct? Because every atom in the electron configuration, the Lewis dot configuration, is going to have a full outer shell. Hydrogens only have one, or only have two electrons in their shell. Yes, dear? Because what I'm given as the starting point is the NH4 plus ion. The plus means that I've lost an electron. So the first step is I've totaled all of the atoms, all of the electrons in atoms, okay? And that comes out to 9. But because of this, this is telling me that I've lost an electron, I have to subtract 1 electron here to make 8. Yes, so this one here, I apologize for the way that this is written. This, this negative should actually be higher. It should be right there. That's where it should be, to signify that this is negative. So let's together, let's go through this. So where's my pencil? Oh, there it is. So in this compound, I have got 1C. So I've got 1 times the number of electrons in the outer shell of a carbon is 4. So 1 times 4 is equal to 4. I've got 1H. 1 times, there's only 1 electron in hydrogen, so 1 times 1 is 1. I've got 2 oxygens. 2 times. Now, how many electrons are in the outer shell of oxygen? 6. Very good. So 2 times 6 is equal to 12. Okay? So if I add these up, I come up to 17. But this here is negative. Tells me I have to add 1. I'll do it like this. I have to add. So now I have a total of 18. Okay? Now this next step is probably the most mind-numbing. Is how do you make something that is symmetrical out of C, 1C, 1H, and an O and 2 O's? Anybody have any suggestions? Yes, sir.
You can put the C and the H, like the H could be on top of the C, and then you can have the 2 O's on either side.
You could. That would be really symmetrical. Turns out you can't do it that way. Can you do it that way? No, maybe you can. Let's test and see. Let's say you're going to have an H here, you're going to have an O here, and O here, right? Okay, so let's start the process. We've got 18, so I'm going to start by putting 1. I have to put 8 around the central atom. That's the first thing. 1, 2, 3, 4, 5, 6, 7, 8. I've got how many left over? 10, right? Okay. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Am I there yet?
No.
No. Why not? Why is this not right?
There's not enough electrons in the valence of the oxygen.
That's right. I've only got 6 electrons on this. This carbon is happy because he's got 8. This oxygen is happy, he's got 8. This hydrogen is happy because he's got 2, but this guy's not. So how am I going to deal with that? Yeah.
Are you able to, oh wait, no. Are you saying about making the hydrogen, taking the hydrogen and oxygen and hydrogen to go to,
Okay, you guys are really good. You guys are doing really good. Okay, it turns out that I think there is a way of doing this. This is in the way, sorry. Oh, sorry, thank you. Let's see. Oh, no. Sorry. So, let's count them up first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. What do you know? We got 18. Now let's see if these are happy. This guy's happy because he's got 8, right? Everybody agreed with him being happy, right? This guy's happy because he's got 8, right? This guy's happy because he's got 8. This guy's happy because he's got 2. Yes.
But in regards to being symmetrical, the H and the C would screw that up.
Is there another way of doing it? Like this is actually true. This is actually true. Okay? This is here. It's called a double bond. Okay? And it does satisfy. But let's see if we can do it another way. I'm going to need a piece of paper. Let's, I did have paper here. Where did I put my paper? Ah! Humbug. What about if we leave that guy there? Let's keep it this configuration and see what we can come up with. So here's C, O, O, and H there. And we're going to put let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. Okay? Is this guy happy? Yeah, he's happy. Is this guy happy? Yeah, he is. Yes, he is happy. He's happy. And this guy, is he happy? Yes, he is. Is this guy happy? Yes, he is. So there's more than one possible configuration of this one. Now, it turns out that these are actually called, sorry? these two bad boys are actually called resonance structures, which means that the electrons can switch, they can flip, they can go back and forth. And so basically what happens is that you have a switching around that goes on. So either one of these things would be considered correct. Now, you're quite right in that, like if you went your way, then this is symmetrical, but there's also an asymmetry here too, because this guy has got two, this guy's got a double bond, this guy's got a single bond. Okay? Now, the last step in drawing Lewis-Dot configurations is that wherever you have a bond, you don't have to, but if it says in simplified forms. So if I did this in a simplified form, can you see that? No, you can't. In a simplified form, wherever you have two electrons, that constitutes a bond. So I could draw this way. C, this here is that guy there. So I'm just going to color it this way. That's this one here. You have an H here, which also has a bond. So I'm going to do that bond like this. I'll just do it in pencil so you can, okay? And so this goes to an O. This one, you have two. This is called a double bond. And so you're going to do this. And you're going to put the O. Now the last step in this is that you have to include all of the valence electrons that are not involved in bonds. So in this one here, what you see is that you've got 4 here, and so you go like this. 1, like so. And on this one, you have 6. So this will go like this. So this is the simplified version. Okay? So this is one of the simplified versions. If I was to do the one up top, it would look like this. Oh, yeah, I'll put it there. Whereas this is the double bond. This is the single bond to the O. And this is the So either of those are true. Is there one better than the other? Not in science 10. They're both equal. Okay? Now, the next one here, HOPO, HOPO. Try doing that right now. Follow the steps. Confer at your desks if need be, and see if you can come up with a Lewis-Dot configuration for whatever that is. HOPO. I have no idea what that is. What? HOPO. I don't know. Just go through the routine.
Why do you multiply it by 4?
What do I multiply what by 4?
Like this one?
Because there's 4 electrons in your shell. Okay, and you look at this, how do you find that out?
Yeah.
If you look at, you find carbon, you see what carbon is? Okay, so above it, it says 4d. That's how many electrons in the outer shell. So if you go next to say
okay.
boron,
Yeah.
it has a 3 above it.
Okay.
So that's 3 electrons in
Oh,
the
you
shell.
multiply it by the number.
That's right. It's however many, whichever column it is, tells you how many electrons in the outer shell.
Okay.
Okay, cool.
Thank you.
Cool.
I have a question.
Yeah.
There's 2 oxygens here.
Yeah.
But there's not 1 oxygen with the 2 beside it. So should I write just 2 times 2? Or should I separate them and write 1 times 2?
You can do either way, as long as you have the right number of electrons, it doesn't matter.
Okay,
Yeah.
cool.
Yeah. Okay. Okay, ladies and gentlemen, can we just step back, because I'm getting the same question here. These numbers here, this is the number of atoms. This is the number of valence electrons. Okay? So, for example, if I look at the first one, nitrogen, the first one, NH4 plus, it's the N tells me I've got 1 N. But how many electrons? If I look here, that 5 there, that tells me that in every one of these guys down here, there are 5 electrons in the outer shell. So that's where the 1 times 5 comes from. If I look at H is here, okay? It is in the column 1. That means that there's 1 electron in the outer shell. There's 1 valence electron. That's why it's 4 times 1. 4 hydrogens, each one has 1 electron. If I go to CHO2, carbon is here. I've got 1 carbon. I've got 4 electrons in the outer shell, so 1 times 4 is 4. Oxygens, I have 2 of those. It's in 6. It's in column 6, so 2 times 6 is 12. Yeah. That's really funny. 2 times 6 is 12. That's where that comes from. And then the final one is, again, hydrogen, 1 times 1. Okay? Does that make sense now? Okay? Are you okay with that, dear? Whoever asked me, was it you, Jacqueline, that asked me about that or no? Do you want me to go through that again? Yeah. Well, just say so then, okay? Jeez. Okay, so which one do you want to look at? Do you want to look at HOPO? Okay, HOPO, H, I've got 1 H, and I've got 1 electron in the outer shell because it's in group 1. So that's 1 times 1, 1 electron. Okay? If I go over to the O's, there's actually 2 O's. They're separated, but there's 2 O's, right? Okay, so 2 times 6 is 12. Do you understand? Do you see the 6 there? Yeah, ignore the 1. Ignore the 1. Okay? So 2 times 6 is 12. Okay? The last thing is the P. P is here. That tells me there's 5 electrons in the outer shell. Okay? So when I add them all up, I've got 1 times 1 is equal to 1. I have 2 times 6 is equal to 12. I've got 1 times 5 is equal to 5. So 5 plus 12 plus 1 is 18. Where have I seen that before? Okay? Sure. So essentially, it's the same as this. Now, when you go to do the electron, the Lewis dot configuration, essentially, you can end up with either the same, but basically the same thing that we just did. So you could have so this is a symmetric representation. So what am I going to do? Well, I'm going to have to put, I've got 18 to deal with, so I've got 1, 2, 3, 4, 5, 6, 7, 8, okay? 9, 10, 11, 12, 13, 14, 15, oh, that's not going to work. I got it. Try it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. No, there's something wrong. Oh, I've got too many on here. I've got too many on here, that's why. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There you go. No, that's wrong too.
You put the, like, fill the whole one, and then there's just no double ones by the
Yeah, that's right. You're right. That's better. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18. There we go. So again, you're going to have a double bond on one side, a single bond on here, and a single bond on here, which is basically what we had on the other one. Okay? So there's a, if you follow the protocol, now you'll never run into something that is this difficult, I promise you. The ones that you're going to be required to do are way simpler. You don't have, there's no real question about what the symmetry is going to be like. You'll see it right away. Okay? So I think at that point you need to breathe a bit. Okay. We've, at the bottom of page 9, we revisit what we looked at on page 1. So I'm going to ignore the bottom of page 9, because that's basically the same thing as here. Okay? So I'm just going to go right by there and just have a quick discussion on carbon chemistry in general. Carbon chemistry is where it's at nowadays. Other than nuclear chemistry, carbon chemistry is where all the research is being done. So this is something that if you were in Biology 12 this year, you would have studied these three guys here. This is we'll call it fatty acid. And you can see that it has carbon, it's carbon rich, it is hydrogen rich, and it happens to have oxygen. So those are the three things, remember, that are the two things that are necessary for organic, is that it has to be high in carbon and it has to have hydrogens involved. And so based on this guy is an organic compound. This is a glucose molecule, which is the smallest form of a carbohydrate you can have. This is the type of sugar that's floating around your bloodstream right this minute. Okay? Now if you look at it, if you look at closely, let's look at closely, you'll see that there is a carbon chain that is linked into pretty much a ring, except this oxygen here. So it does have carbon. It is rich in hydrogens. Okay, but it also does have oxygens. But oxygens aren't necessary for it to be organic. It's just necessary to be carbon and hydrogen rich. This guy is an amino acid. It's the building block of all proteins. Okay? It's an amino acid because this is called an amino group, NH2. This is C double bond OOH. It's called an acid group or carboxylic acid group. And it has, as you can see, it is carbon and hydrogen rich. So here are the carbons. Here are the hydrogens. And it does happen to have oxygens as well, but it also has nitrogen as well. But it still is an organic because it's carbon-hydrogen complement, okay? That's basically it. So the moral of the story here is that if I show you a molecule, you need to look for carbons and hydrogens to answer the question, is this an organic chemical or not? If it has carbons and hydrogens, the answer is yes. If it has carbons and oxygens, just oxygens, no hydrogen, the answer is no. Okay? That's where they're going to trick you. All right? Okay. Any questions on that? Mostly review, right? Everybody's okay with that? Okay. It has to have carbons and hydrogens to be considered organic. It can have other things, but it must have carbons and it must have hydrogens. Okay?
Wait.
Yeah.
So does that mean we can make organic substances in a lab?
We can. Not easily.
No lab.
The first organic chemicals that were made is something called urea. Okay? Now, up to the time when urea was synthesized, it was believed that only living things could make living molecules, or organic molecules. Okay? They can be synthesized. Okay? I think urea is something like that, which is still organic. It's a very simple organic molecule. Yes, dear.
If it has oxygen, does that mean it's not?
No, it can have oxygen.
Yeah.
Yeah, if you look over here at carbohydrates, these guys have oxygens as well. Okay?
And that's still organic.
It's still legit. But what you have to key on is it has to have carbon, and it has to have hydrogens. If it's missing one of those, it's clearly not organic. Okay? That's what makes this organic, is that it does have carbons and it does have hydrogens. The fact that oxygens and nitrogens are there has no bearing on it. It's the carbons and the hydrogens that make it organic. Okay? Now, the really cool thing about why is this carbon such an important thing is if you look on this page here, and if you look on the periodic table, we talked about this earlier on, is how many electrons does carbon have in its outer shell? Has 4 singles, which what that means, it means 2 things actually. It means that it can form 4 bonds. It also means that these will form perfectly symmetrical tetrahedra. Okay? And it's not necessarily that you have to have carbons bonded to something else. You can have carbons bonded to carbons, to bonded to carbons, to bonded to carbons, to bonded to carbons, to bonded to carbons. There's actually an organic chemical. I'm going to see if I can find this. This guy here. Can you see the name on it? This is 60 carbons in this thing. It's called Buckminster fullerene. And you notice how it is assembled. Now, what they don't show are the hydrogens that are coming off of this. Because if you look at this, if you look at this here, if you look at this carbon here, it is bonded to 3 other carbons, right? Now, this is fullerene, so one of these bonds is going to be a double bond. So this is an actual chemical composed of nothing but carbon. This is not carbon nanotubules and stuff like this, but it's based in the same way as carbon nanotubules. Okay? Buckminster is the name of a guy. Like, you guys are so young. You're so young. Growing up in the 70s, there was an architectural, event that occurred where geodesic domes came into vogue. Houses were actually built on this structure. And in fact, some structures still are. Things that are like radar domes are built on Buckminster fullerene design. The Buckminster Fuller is actually the name of a guy. He was the guy that invented geodesic architectural design. And he based it on this. So this C60 molecule is actually named in his honor. Okay? Very cool stuff. But it is, they refer to these colloquially as buckyballs. So if you ever hear the term buckyballs, it's because of this and Buckminster fullerene. Buckminster Fuller. Buckminster is the guy's first name. Fuller is his second name. Okay, so they just put them together. But what this means is that you can actually have an infinite number of possible compounds in organic chemistry. There is no limit. There is absolutely no limit. And that's why, other than nuclear chemistry, the biggest area of research is in organic chemistry, because all drugs are based on this. Every drug in your cabinet, every vitamin, everything, with not minerals like magnesium, calcium, those are minerals, those are found in the periodic table. But everything else is an organic chemical, and some of them are extremely large, like huge. I don't have I had to change my iPhone, but on my iPhone that I had before, I had an app on there that was organic chemicals in 3D. You can tell who the nerds are, right? They have those kind of apps. But if you put it, you could put down, like, say, aspirin. Put aspirin and look at the chemical. That's aspirin, acetyl salicylic acid, ASA. Okay? So you have a 6-carbon ring. So you have at every corner here, carbon, 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 carbon. Off this guy, double bonded O, single bonded O off these 2 carbons, and a hydroxyl group. Actually, this is the acid group. This is carboxylic acid. C double bond OOH. That's the acid group. ASA. Yeah. Oh, whenever you have a change of direction like that, or a terminal line like that, that implies that there's a carbon there. So on this one here, there's a carbon there. It's bonded. It has 1 bond here, 2 bonds here, and that means off here there's going to be an H bond. Look, okay. Let's go here. Let's go to the next page. Hold that thought. I want to go to the next page, and this will explain why. Okay. At the top of the page. Oh, you can't see that because I don't have it up. Come on. I know you're in there. Okay. At the top of the page, when we talk about organics, you said we will always have a carbon chain. You will always have multiple what's the other thing you always have? I don't know, I can't remember. Because it says you could also have these. You can nitrogen, sulfur, halogens. Well, this should be, and you always have, no, this not always, always, but commonly have oxygen. Okay? Now, it turns out that there is, no, I don't want you to go there yet. I want you to look at this. Here are the rules for organic chemistry. carbon must have 4 and only 4 bonds filled. Nitrogen must have 3 and only 3 bonds filled. Oxygen must have 2 and only 2 bonds filled. Hydrogen can only have 1 bond. Maximum. Okay? Now, this here is a, are you okay? I see that panic look in your eye. Are you panicking, my dear?
Just a little bit. Just a little. How many what?
4, this one here, carbon must have 4 and only 4 bonds.
No, in organics you always have.
Oh, carbon chain, multiple hydrogens, and commonly oxygens.
Okay, cool.
You can have other stuff, but they come and go. Okay? Okay, let's look at this diagram down here. And this is really a bunch of gobbledygook that nobody in his right mind wants to have to draw, especially chemists. Chemists are notoriously lazy, okay? So if we can find a way to draw something simpler, we will. So what we do is, instead of drawing each individual carbon and each individual hydrogen, what we do is we make it simpler. For example, if I wanted to draw this, what you see, well, I'll scooch in a little bit so you can see that. No, this is just by way of explanation so that you understand what's going on. Okay? Come on, light. This is butane. That's butane. Okay? Now, nobody in his right mind wants to keep having to draw that. So what we do is we invoke a shorthand that looks like this. That's butane.
Wait, what?
This is the same as that.
That's hilarious.
That's what that means. Okay? So wherever there is a corner, so wherever there's a corner, or wherever there is a terminus, terminus means an end of something. If there's nothing there, that implies that a carbon lives there. Carbon lives there, like that. So you can see it starting to take shape. Okay, what about the hydrogens? Well, again, it is understood that if there is nothing there, the empty bonds must be filled by something. Therefore, it must be filled with a hydrogen if nothing is stated. So that implies that off of this guy, there must be 2 hydrogens. Why? Because the carbon must have 4 and only 4 bonds. It's the rule. You can't get around it. So that must be true. This guy must be true that he has like so. Well, what about this carbon? He's only bonded to 1. Well, that means that he's got to have 3 other hydrogens. Because the law of the land says that a carbon must have 4 and only 4 bonds. Okay? If you look at him, he's at present, He's only got one bond right here. So the rest has to be filled with something, so it's going to be filled with hydrogens. And so the same is true of the other side. So this is a super shorthand. You say, well, why are you teaching us that? Well, I'll tell you why. Okay? Because you're going to have to draw what we call isomers. An isomer is a version of an organic chemical that has the same chemical formula but different chemical structure. For example, let's say I can find my clock. Okay? Let's say I wanted you to draw all the chemical structures, the possible chemical structures of, I don't know, let's say pentane. But I'm not, because you guys have never drawn, you don't know what pentane is. You maybe heard of pentane before. I'm going to tell you that pentane is a 5-carbon chain, and everything else is hydrogen. So that means that it's going to look like this: 1, 2, 3, 4, 5. And because each one of these has to have 4 bonds, that means that I have to fill it with hydrogen. So here's a hydrogen. Here's a hydrogen. Here's a hydrogen. Here's a hydrogen. Hydrogen. This is starting to get really frustrating and repetitive. If I said octane, you'd have to have done 8 of those. So thank you, lucky stars, I don't want to say oh. If I said to you, draw all the possible structures of this, well, I'm going to show you one structure. Okay, so the question is this the same chemical formula as this? Well, 5 carbons, so I got 5 carbons there. How many hydrogens do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. How many carbons? 5. How many hydrogens? Start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Both C5H12. But they're different. And here's the rub with this. In real life, these have different properties. Okay? This is called N-pentane, this is called isopentane. They have a slightly different flash point, they have a slightly different melting point, they have a slightly different density. A lot of things are slightly different, so they're not the same thing. Now, there are other versions of this. Now, to try to figure out what they are, using this doodling is mind-numbing. It's like, so I said to you, okay, what about this one? Is this the same as that? This is the same. Yes, it is. Why? Because all I've done is I flipped it in 3-dimensional space. If I had it this way or this way, it'd be the same thing. So what is the easy way of drawing these? The easy way is this. 5 carbons. 1, 2, 3, 4, 5. Ignore the hydrogens. Who cares about the hydrogens anyway? Because they're going to find their own place. So now I say, okay, well, how can I draw this? Well, if I take this guy off here and put him here, that is him. 4 carbons in a chain, 1, 2, 3, 4. Off the second carbon is another carbon, here. Okay? So if I did this, this is the same as that, and it's easier to see because they say, duh, flip, flip. Nothing to it. What is the other? Now, just what I did there. There is one more isomer that you can draw from this guy. What is it? Anybody? Anybody can venture some of that? Say again? No, that's a very, very good shot throw. The reason why it can't be a square or a 5-sided is because we don't lose 2 hydrogens. See, if I did this, I have the 5 carbons. But what about the hydrogens? Well, these are all bonded, so I have a hydrogen here, hydrogen here, hydrogen here. Full. How many hydrogens? And it can't be the same, it has to be 12. So if you form a cycle, then you lose 2 hydrogens. Here.
So you're like, 1, 2, 5 carbons.
Yep. This one? This one here? Which one? This one? This one? This one? This one?
So is the little line between the seams also the hydrogen?
Between, no, that's their direct bond. There, this carbon bonded to carbon to carbon to carbon.
Okay. So it doesn't matter, because only 4 bonds, yeah? So it doesn't matter if it's like the same.
Yeah, as long as it's 4 bonds.
Oh, okay.
Yeah. Okay, I'll spare you the agony. The only other thing that you can do is let's take this guy one more step. We take this guy one more step. The only thing I can do is I can take this guy off and I can put him here as well. Now it's not going to look exactly like that because of electron-electron repulsion. It's going to change its configuration so that if I try to draw this in a 3-dimensional thing, oh, sorry. Okay, so how you read this? What this means is that this carbon, and this carbon are in the plane of the board. Okay? This carbon is coming out at you. It's coming out at you. This carbon is receding into the board. It's going behind the board. So this is true. Now, if I added the hydrogen, this carbon has got 4 bonds, so he's got no hydrogens at all. This carbon has to have 3. So I'm just going to write CH3. Do you mind if I just do that instead? So this is going to be, he's going to have 3. He's going to have 3. He's going to have 3. And he's going to have 3. Okay? Like that. How many hydrogens? 12. How many carbons? Careful. 5. It's the same thing. It has the same formula, but it has a different structure. So this is equivalent to this, to this, to this, so far as what it's made up of. But they're 3 very different chemicals. Okay? Now, going back to this, what I did here was, this is a bit of a game, actually. The game, these are the rules of the game here. 4 and only 4 bonds for carbon, 3 for nitrogen, 2 for oxygen, and 1 for hydrogen. What you're challenging here is to determine where the mistakes are. And there's a whole bunch of mistakes here. Okay? Two bonds, double bond. Do what it says. Circle as many as you can and say why. What's the problem here? Give you 3 minutes.
Checking between
Yeah, those are only 2 bonds.
there's something number on
Yeah,
here. Nitrogen.
yeah, you're missing a bond, you got it right. That's right.
Between the nitrogen and the oxygen,
That's a bond.
there's a bond, so they don't have to have it. I mean, it'd be confusing if it didn't have all these on it.
Don't throw the word God.
So, what about this one? Because that is.
That, yeah. No, no. We're dealing with atoms now, we're not dealing with polyatomic atoms.
Okay, so it's
This is organic, it's not ionic. Yep, that's right. That's right. Okay, so you got it. That's right. That's right. That's right. That's right. That's right. That's right. You're there. Come on. Okay, so the green ones have the correct number of bonds. The red ones don't. So if we start at 12 o'clock and go counterclockwise, this is only 3 bonds, so it needs one. So this needs one more. This one also has only 3 bonds, so it needs one more. This one has 3 bonds. This is a double bond and a single bond here, so it needs one more. This one here has got 5 bonds, so this is should be missing a bond. This is missing a bond, so I have to add 1 there. Okay, because nitrogen needs 3, so 1, 2, should have something else here. This one's fine. 1, 2, 3, 4. On this one, 1, 2, 3, 4. This oxygen has got 3 bonds. 1 there, and 1 to the hydrogen. So it's got 1 too many. Okay? Okay. So you guys have got a bunch of homework to do, apparently. If you have not already done the pH scale, how many have done this and had it in? Okay, so one of us, 2 of us. Okay, what do you call it? It has instructions embedded in here, so you just follow the instructions very strictly and you'll be fine. So it says, subtract the lower pH from the higher pH and multiply by -1. Okay? So for example, if you have pH 5 and pH 7, 5 minus 7 is -2. Then you multiply by -1 and you end up with 2. So N becomes 2 in 10 to the N. Okay? 10 squared is the same as 10 times 10, which is equal to 100. So therefore, a solution, ladies, of pH 5 is 100 times more acidic than a solution with pH 7. I'll do one more. Following the instructions, you subtract the lower from the higher from lower. So 1 minus pH 1 minus pH 3 is equal to -2. You multiply that by -1 is equal to 2. So 10 to the 2 is equal to 10 times 10 is equal to 100 times. Okay? Simple. It's just straight like that. Okay? That's all you do. You can do that. That's so simple. Okay? 8.2 starts, I believe, yeah. 8.2 starts with doing Bohr diagrams and Lewis diagrams for both atoms and ions. So let's look at hydrogen, for example. The number of valence electrons in a hydrogen atom is 1. So the Bohr diagram is like this. Okay? For atoms, the Lewis dot is simply like that, or you could have it anywhere else. Just hang a sec. For an ion, there are 2 possible ions. Coal. I'm doing this for your benefit as well as the others. Don't rob from them and don't rob from yourself. There are 2 possibles. Because the hydrogen wants to get a full electron shell, it is either going to gain 1 or lose 1. So it can be either this, if it loses 1, hydrogen, just get proton, or it can be this. Magnesium. How many electrons? Magnesium? 2. The Bohr diagram. Lewis diagram for an atom. For an ion, what's it going to do in order to become an ion? What's magnesium going to do in order to become an ion? Yeah.
You want to basically take away those 2 electrons.
And what are you left with?
The previous
That's right. The next shell down. What does the next shell down look like? That's right. So for an ion, okay, now as you go through these, you're going to find out that for ions, you're going to have, all of them are going to have a full outer shell, as you would expect. Because if you do the same thing for a Bohr diagram, you end up with all full outer shells. Okay? On the second page, you're asked to do you're asked to do molecules, 1, 2, 3, 4, 5, 6. This one is a misspelling. This should be not carboon terachloride. This should be carbon tetrachloride. So what we did at the top of the class, you need to do for these. Santa. Okay. Mr. Houston, can I get you to distribute one of each? Okay, you have another item. In addition to that, there are two sides to this page. There's a little bit more practice on here. Okay? And then on the back side, flip over the back side, there's this. It says, use the structural formula of the butane molecule to answer the questions. Number one, what's the chemical formula for butane? What do the straight lines in the structural form represent? There's another structure that could be drawn which also contains the same number of carbon and hydrogen atoms as the butane molecule. Explain now how this fact illustrates the uniqueness of a carbon atom. Draw the structure and draw the structures below. Okay? Now, in order to draw the structures below, you have to invoke the rules. Carbon has 4 and only 4. Nitrogen has 3 and only 3. Oxygen has 2 and only 2. Hydrogen has 1 and only 1. You have to invoke that. Okay? And for the last one, we've already done this in class, but draw the 3 structures of pentane. Okay? So this is due for tomorrow. Okay? Tomorrow in class, what I would like to do is I would like to go through this. Through all this homework stuff. So tomorrow is going to be largely looking at what we've done. There's also Chapter 8 review. There's also a Chapter 8 review document. You don't have to do it from your thing. And there is a CYU 8.3, which is found in Moodle. So tomorrow is going to be a correct what I've done, work on more stuff, and make sure I understand what the heck is going on. And you won't be able to do that if you go home tonight and do none of this. If you go home and do none of this, you are totally screwed. You're done. Do it again next year. Okay? You need to do this. Tomorrow, I will also, if you finish everything, I'm going to give you time to do the chapter review. Chapter test for this. It's Friday. We are going to start on Thursday. We're going to start chapter 9 on Thursday. So batten down the hatches. Like I said, welcome to Science 10. Science 8, Science 9, Science 10. Get used to it. It's not slowing down until the end of June, beloved. You're welcome. Yes.
I don't have that first one.
Oh, this one here? This one here? How many need this? The which one? Oh, the pH scale, this one here? How many need this booklet? I have 4. You need 5? Okay. 6. Going.
Oh, reprint?
7
Wait, for the reprint stuff?
for these things.
Yeah. Oh.
7 going. 8 going. 9 going. Okay. 1, 2,
Wait, what is that for?
3, 4. There's 4. There's 4. I will go print another 5 or 6. Thank you, dear.